Welcome students. Now we are going to see the next concept. Now next concept is complete matrix space. Now we are going to see now definition of complete matrix space and some examples of complete matrix space here. So first definition of complete matrix space. Students, we know that in matrix space, Cauchy sequence need not be convergent. So that's why this concept is important, because in this case, we write here, now a matrix space X comma D is said to be complete if every Cauchy or Cauchy sequence in X is convergent. That is, if X is complete matrix space, then every Cauchy sequence in that matrix space is always convergent. So in other words, so we can write here, if XD, now this is a complete matrix space, is a complete matrix space. If whenever the sequence xn in X such that d of xm comma xn, now this tends to 0 as m and n tends to infinity. Here there exists an element x belongs to x, so with now d of xn comma x, now this tends to 0 as n tends to infinity here. Okay, now students, we know that if xn is a Cauchy sequence in a matrix space, then xn is convergent if and only if it has a convergent subsequence. So using that, we can write one more statement. Now that statement is that a matrix space X comma D is complete if and only if every Cauchy sequence in X has a convergent subsequence. Now we are going to see example of complete matrix space. Now students, we know that now the set of real numbers with the usual metric, that is d of xy is equal to absolute value of x minus y. Now R is complete here. R means set of real numbers is complete matrix space here, because we know that if you take a Cauchy sequence in that set, then that Cauchy sequence is always convergent here. So we are going to see the detail of that. Now we are going to see that the metric space or the usual metric space RU is a complete metric space. So we are going to see how RU is complete metric space. So in this case, now we are going to take a Cauchy sequence and we are going to prove that that Cauchy sequence is convergent here. Okay. Now if Xn is a Cauchy sequence of real numbers, then we know that now limit n tends to infinity of superior of Xn now and limit n tends to infinity of inferior of Xn are real numbers here, are real numbers. Okay. Now we are going to show that now this sequence is convergent here. Now remember that now since Xn is Cauchy sequence of real numbers, then that sequence is bounded. Now remember that if you take a metric space, then in that metric space Cauchy sequence is always bounded. Now here in particular we are taking X is equal to R here, that is set of real numbers. Now we also know that limit n tends to infinity of inferior of Xn. Now this is less equal limit n tends to infinity of superior of Xn here. Now say this as 1. Now this is first inequality. Now since we want to show that now this Cauchy sequence is convergent, so we'll have to prove that limit n tends to infinity of superior of Xn is equal to limit n tends to infinity of inferior of Xn, that is limit of Xn here. So we need to prove that here limit n tends to infinity of superior of Xn. Now this is less equal limit n tends to infinity of inferior of Xn here. So we want to prove this. Okay, for that now we are going to use this. Now we know that Xn is a Cauchy sequence of real numbers here. Now since Xn is a Cauchy sequence so we write here, given epsilon greater than 0, there exists a positive integer capital N such that we write here absolute value of Xm minus Xn. Now this is less than epsilon by 2 for all m and n greater than or equal to n. And so we write here, now here we are taking now m is equal to this small m is equal to, we are taking capital N. So we write here absolute value of Xn minus Xn. Okay, this is less than epsilon by 2 for all yes, n greater equal capital N here. That is, we can write here now absolute value of xn minus xn, this is less than epsilon by 2 for all n greater equal n. So we can write here now xn minus epsilon by 2, this is less than xn is less than x suffix capital N plus epsilon by 2 for all n greater equal n here. Now it follows that now here, now this is xn plus epsilon by 2, now this is the upper bound here, and xn minus epsilon by 2, now this is the lower bound here of the set x suffix capital N, x suffix capital N plus 1 and so on. Okay, so it follows that now this xn plus epsilon by 2 and xn minus epsilon by 2 are respectively upper and lower bounds for the set here. Now x suffix capital N, then x suffix now n plus 1, x suffix n plus 2 and so on. Hence now using this we can talk about now this. Hence if n is greater than or equal to capital N, so we write here now xn plus epsilon by 2 and xn minus epsilon by 2 are upper and lower bounds for the set here xn plus 1, xn plus 2 and so on. Okay, now this contains now terms of the sequence xn here. Now this implies that now we have now xn minus epsilon by 2, now this is less equal, now greatest lower bound of or GLB of xn comma xn plus 1, xn plus 2 and so on. Now this is less equal, now list upper bound of now xn comma xn plus 1, then xn plus 2 and so on. Now this is less equal, now this is the least upper bound, and we know that now xn plus epsilon by 2 is upper bound of this set, so we write this. Now using this inequality we can write xn minus epsilon by 2, now this is less equal greatest lower bound of this set, so we write GLB of xn comma xn plus 1, xn plus 2 and so on, and we can write here now list upper bound of this set xn comma xn plus 1, xn plus 2 and so on. Now this is less equal, now xn plus epsilon by 2. Now if you multiply this by minus 1, okay, then you can write here now this is okay, you can write minus xn plus epsilon by 2, now this is greater equal minus GLB okay of xn comma xn plus 1, xn plus 2 and so on. Now adding these two we write here, so we write here list upper bound of xn comma xn plus 1, xn plus 2 and so on minus greatest lower bound of xn plus 1, xn plus 2 and so on. Now this is less equal. Now actually epsilon by 2 plus epsilon by 2. So we simply write here epsilon because we have here minus xn and plus xn. Okay, so we write here now simply this is less than or equal to epsilon. Now taking limit on both sides as n tends to infinity here. Now taking limit on both sides, then we obtain actually limit n tends to infinity of this is nothing but limit n tends to infinity of superior of xn, and actually this is minus, okay, limit n tends to infinity of, now GLB of this set, it means that limit n tends to infinity of inferior of now xn. Now this is less equal epsilon. So therefore we write here limit n tends to infinity of superior of xn, this is less equal limit n tends to infinity of inferior of xn plus epsilon. But epsilon is arbitrary here, that is epsilon is very small quantity. So we write here since epsilon is arbitrary, so we write here limit n tends to infinity of superior of xn. Now this is less equal limit n tends to infinity of inferior of xn. So this is 2 here. So using 1 and 2, yes, we can write limit n tends to infinity of superior of xn is equal to limit n tends to infinity of inferior of xn. So we write here from 1 and 2, we have here limit n tends to infinity of superior of xn is equal to limit n tends to infinity of inferior of xn. So it means that here when sequence is convergent, then we have limit n tends to infinity of superior of xn is equal to limit n tends to infinity of inferior of xn. So therefore we write here limit n tends to infinity of superior of xn is equal to limit n tends to infinity of inferior of xn is equal to now limit n tends to infinity of xn. So this tells us that now this sequence, okay, xn is a convergent sequence of real numbers. So this tells us that every Cauchy sequence of real numbers in R with respect to usual metric is convergent. Hence RU, that is this set, okay, R with usual matrix, that is the metric space RU, is a complete metric space here. Now second example is that now the usual metric space CU, okay, CU, it means that C is the set of complex numbers. Now that is also complete. Okay, so second example is this. Now second example of complete metric space is this. The usual metric space CU is complete. Now to prove this, you will have to show that every Cauchy sequence is convergent in set of complex numbers. So we take a Cauchy sequence now in C, that is in the set of complex numbers, or we take a Cauchy sequence of complex number, and we are going to show that that sequence is convergent here. So consider this. Let Zn. Now remember here Z, I am taking Zm. Zm. Now Zm, it means that here we have xm plus Iym. So where xm and ym are the sequences of real numbers here. Xm and ym are the sequence of real numbers here. So be a Cauchy sequence of complex numbers. Okay, where now these two sequences, now where xm and ym are sequences of real numbers. Now Zm is a Cauchy sequence. So by using definition, we write here, then for each, we write for given epsilon greater than 0, yes, there exists a positive integer, now capital N here, capital N, such that here now absolute value of Zm minus Zp, this is less than epsilon for all m and p greater than or equal to n. Now we know that now absolute value of Zm minus Zp, it means that here we can write absolute value of now xm plus Iym minus xp plus Iyp. So that is, we write here absolute value of xm minus xp plus I into ym minus yp. So using now definition of modulus of a complex number, we write here this is nothing but square root of xm minus xp bracket square plus ym minus yp bracket square. Now using this, we write here now square root of xm minus xp bracket square plus ym minus yp bracket square. Now this is less than epsilon for all m and p greater or equal n here. Now on squaring both sides, we write here, now we want to remove this square root sign. So we write here on squaring both sides, we get here xm minus xp square plus ym minus yp square, this is less than epsilon square for all m and p greater or equal n. So this implies that actually sum of the squares of these two terms is less than epsilon square. So we write here xm minus xp bracket square, this is less than epsilon square, and ym minus yp bracket square, this is also less than epsilon square for all m and p greater or equal n here. So therefore we can write here, yes, absolute value of xm minus xp, now this is less than epsilon, and absolute value of ym minus yp, this is less than epsilon for all m and p greater or equal n. But we know that xm and ym are the sequences of real numbers. So we get here now xm is Cauchy sequence and ym is also Cauchy sequence here. So this implies that here xm and ym are Cauchy sequences of real numbers here, of real numbers. That is actually xm and ym are the Cauchy sequence in R. R it means that set of real numbers with usual metric here. But we know that, but R is complete here. Now R is complete. Just we have seen. Okay, R is complete. That is RU is complete metric space. So this tells us that now these two Cauchy sequences are convergent. So this implies that now xm converges to x, say, and ym converges to say y. Okay, now since R is complete metric space, it means that now these two Cauchy sequences are convergent here. Okay, so this implies that now this sequence xm, which is xm plus iym, so now this sequence converges to say z, which is x plus iy, as m tends to infinity here. So now here, now this Cauchy sequence is zm, okay, now is convergent and it converges to z, which is x plus iy. So using this, okay, now we can say that now every Cauchy sequence in set of complex numbers is convergent. So therefore we write here Cu is the complete matrix space here, matrix space here. Okay, thank you.